Okay, let's take a look at what we have learned. And last time we have learned something about the center difference, how to do the center difference to approximate the. So last time we have already learned how to do the center difference formulas to get the, check my speaker. What's happening? Continue without audio. Okay, good. So let me double check the setting once again. Okay, good. And last time we have already done the center difference formulas for the approximations of the first derivative, and we got at the end of the analysis we have the error is a second order's h. And this time let's take a look at this one, and we have, so this is the second order of h. And how do we derive this formula? We are using the Newton's font to derive this formula. And last time we also mentioned something about the rounding of errors in the numerical differentiations. And we briefly mentioned that we actually used a lot of time to analyze this. And that's the errors, the total errors in the approximations of the second with using the center difference formula. And the total errors, it contains 2 parts. One is the truncation error for using the center difference formula, and then another error, it contains the realm of errors in the computer. And we have, if we want to minimize the total error, we need to do a trade-off. We cannot keep decreasing the h, because if we keep decreasing the h, and then this part of the h, the error, this is the round of errors, this part would increase. So we are doing some trade-off here, doing some balance between these two terms. And so if we want to minimize these errors, and then actually we want to do a minimization of this function is about the h. It's a function of the h function. And so we do a minimization of this total error, and then we got, this is the optimized h step size. And last time you asked me the questions, why do I change this one to the infinity norm of the third derivative? And actually we can find this third derivative with the maximums. This means the maximums on the interval. So this one is bounded by the maximums of the third derivative. And then so if we use this to, we say this is the bound for the error, the total error, and then we want to solve the minimizations for this bound, and then that's the optimized step size. And that's some things we have learned in the last course, in the last class. And today we are going to do some things more excited. So as I said, let me just copy them, what we have here, the forward difference formulas, and then I cannot remember what's the, actually, I cannot remember what's the order of the forward one. Let me see. Do we have something here? Not really. We don't have something here. So let me see. Where's the first formula? Corrected. Okay. Let's go to take a look. The finite difference. Okay, so this is the forward and backwards. This is the forward difference formula. And let's just copy down the errors. Here we have H order, H with the order 1. And this is the errors for the forward difference formula. And then we say the forward and the backward are pretty similar. And then they have the same magnitude of the error. And then they have the H to the order 1 error. And we also analyze the center difference formula, and then as we just do the review, and then we have the errors for the center difference formula is the order of 2, and both for these 3 formula, we are approximating the first derivative at the point. The first derivative at a point. Today, what we are going to do, we are going to divide one formula, and that is with higher order of the accuracy, and we want this. We want higher order, and then maybe we can do derive formulas, and then such that it has accuracy with order of 4. So this is the first part of today's discussions. So that's the Richardson's extrapolations. We use these methods to get the high accuracy formula to approximate the first derivative. And so today, this one is still approximating the first derivative. And we are using a different way to derive the formula. From the formula, forward difference formula, center difference formula, we are using the Newton's form to get the approximations to the F. And today we are using the Taylor expansions to approximate the F. And then let's take a look at here. What's the Taylor series? Taylor series is Taylor series of the real function is infinite differentiable, which is infinite differentiable at the neighborhood and of real number A, and then it's the power series looks like this. So the Taylor series is in this way. We can approximate the fx in the neighborhood of the A if the fx is infinite differentiables in the neighborhood. And then we can use the Taylor series to approximate it. Of course, we have the convergence radius, but let us skip the discussions for the radius, convergence radius in this class. And we just assume that we have a small enough neighborhood around the A, and then we can approximate that we have such an, we can represent the fx with this Taylor series. And so now let us derive the center difference formulas with the Taylor expansion. So in previous classes, we have derived the center difference formula, but it's with the Newton's form. Today we are going to use the Taylor expansions to derive the center difference formula again. You will see I'm deriving this again, and this is because we would use this uses the derivations in when I would use this derivation here to get the Richardson's extrapolations. So let's take a look at here. If we want to derive the center difference formula, let's go back to the center difference formulas. What do we have in the center difference formula? We have two things. We have the fx0 plus h, right? And then minus fx0 minus h divided by 2, right? So now let us do the Taylor expansions for this one, and also do a Taylor expansions for this one. And so let's see what do we have here? We have fx0 plus h. So I'm going to just use this Taylor series here for this one, and I am replacing the x0 plus h with the x here. And the a here is actually taking us the x0, and the x here I'm taking the x0 plus h. So that I have, for the first one, I have fx0, and then the second term, I have the first derivative term, and then times the h, and then plus the third term, it should be the 1/2 factorial, and with the second derivative, h squared, and then 3 factorial, third derivative, and it's pretty simple. And I have the h3, h something here. That is because x here plus h and then minus, because this is x0 and then x0 much plus h and then minus x0, and then that is just h with the order of n. So now I got, and I also have the fourth term, and I'm going to write a lot of term here. And I also have the fifth derivative here. And this is, and I am skipping the terms coming after. And so this is the Taylor series, Taylor expansion for the fx0 plus h. And let's take a look at the second term. And this is the second term here. And we are doing the same thing, doing the getting the Taylor expansions for it. We have the first one, but this time you need to be very careful because we are changing the style. So the second term, it should be minus fx0h. And then the third term is still the plus side. And then the third term should be negative, the minus side, because we have, this time we have minus h here, and not the plus h. And so we also have the fourth term, and the fifth term is also with the, because this is the odd number, and then we have odd order, and then we have the minus side here. And these are the Taylor's expansions for these two terms. And then the next things we are going to do, so let's say this is the formula 2, formula 1, and then we are subtracting the 2 to the 1, from the 1, and then we do the subtractions there, and then we got on the left-hand side, you will see there's some cancellations here, right? And we have the fx0, fx0 here, and then it would be canceled. Let me see. Actually, I am subtracting the 1 from the 2. It should be subtract the 1 from the 2. Subtracting the 2 from the 1. Okay. And you will see some cancellation here. The x0, fx0, and then all the E1 order term, the E1 order term, the h squared term here, and then the E1 order here, and then we are still canceling them because they have the same sign in these two formulas. And subtracting the 2 from the 1, and then we got, so at the end, we got fx0 plus h minus fx0 minus h. And with all the cancellation here, the E1 order term just disappear. We have on the right-hand side, we have double f prime x0h, and then double 2, 3 factorial we only have the odd order term here, and then 5 factorial f5 x0, and then to the h to the 5 order 5, and so on and so forth. We have more terms coming after this. So now let us divide both sides by 2h, dividing both sides by h, 2h, and then we got this. And I'm moving the upright x0s to the left-hand side, and then move all the other terms to one side. And then I got upright x0 is equals to, so I'm going to divide both sides by this 2h. And this is something you have already seen before. This is just the center difference formula. And the terms coming after it is the error. It's the error if you're using the center. We still have some terms coming after it, and then that is the fourth order, because we are dividing the 2h here as well. So 2 and h. So this error term we have h to the order of 2, and then this one is these terms divided by 2. And then also I'm changing the sign because I moved the things to one side. And okay, and also we have more error term here, but that's not important because the terms coming after it is with higher order, and then this one is the dominant error term here. So now you've got the center difference formula, and then but with another way, we are using the Taylor expansions at 2 points. One is at the x0 x plus h, and then another one is x0 minus h, and then we do the subtraction and divided both sides by 2h, and then we got the center difference formulas in this way. And these are the error term. And why do we get why do we deriving the center difference formulas with another way? Because this error term would be more useful in the derivations of the Richardson expansions, extrapolations. And later on, we are going to use this error terms. And so this means that we can write the upright x0 and then plus this is the this one is just the center difference formula, right? And then and we have already used one notation to denote it. It's the dh0. dh0. This one, it means center difference, and then this one is the step size we are using. And we are going to use some notation, some symbols to replace the number, the exact values here. And then we are going to denote it as the C2, because I'm using the subscript 2 here because this is the order 2 error term. And then we have one more error term, and then this is a C4, H4. And I am still using the fourth subscript here because this one is corresponding to the fourth order error term. And then I'm skipping all this error here because it's dominated by these 2 error terms. And so this is the center difference formula, and then is highlighted in the purple here, the purple area here. And this is just the formula. I'm replacing the formula with the notations here. And then these are the error term and next. So once we have such a formula, let's take a look. What can we do with these two expansions? We can still do something else, but it's not I'm doing something else with these two expansions, but this is not about the Richardson's extrapolation. I am going to use this two Taylor expansion here to derive a formula to approximate the second derivative. So you can see if I subtract them, right? And then you will see the odd number terms would goes away, right? And if I do the plus here, and then what can we do? Get we keep the E1, and then if we do a plus for this two formula, additions for this bottom formula, and then we keep the E1 order term, and then remove all the odd number term, odd order term. So let's do the additions for this two formula. We add the 1 and 2, and then we obtain this. So this is the Taylor expansion, the sum of these two Taylor expansion. And then because the cancellation, we only kept the E1 order term. And so we also have the fourth order here. This is another part. I'm deriving the formula for the second derivative to approximate the second derivative. Okay, we have more terms coming after this, but let's skip the writing for the terms after this. So now my question is that let's use these things to approximate the second derivative. So I'm going to solve for the second derivative with this formula, and which means that I am going to move these terms to the left-hand side, and then divided the things by h squared. So here, if I do, okay, I'm going to move the this term, the 2fx0 to the left-hand side. And then I got the minus 2fx0, and then plus fx0 minus h. And divided both sides by the h squared, and then I got h squared here. And then on the right hand side, I have f2x0, and then plus, so I'm dividing the both sides by h squared. And so this is just the 2/4 square, 4 factorial. And then we have only 2 order left because it's divided by the 2 order 2h. And then we have only 4 order left for the 6 order term. This is some things we got here. So at the end of the day, if you reorganize these things, and then you would get this, which means that we can approximate the second order term with such a formula. But with the error here, minus the 2 6 factorial f6 x0 h4. So this means that we can use this formula to approximate the second derivative, but these are the error term for this formula, if we use the formula to approximate the second derivative. So let's make this clear. And this is the, I'm using the notation here to denote this formula. And once again, the subscript is for the step size. And then I use the 2 here because it says this is for the second derivative. And here I have, this is the second derivative formula. And then I'm using some constant to represent the errors I have here. And I'm using the same system, but I use the tutor to here. here to represent this is another constant, which is different from the constant we use here. And this is one constant, and then H2, and then plus another constant, and that is H4. And this is the second order. This is the second order approximation because the error time is dominated by this H2 the order of 2 error. So, which means that this is approximation, a second order approximations for the second derivative of the f. So these are totally 2 different parts, but we use Taylor expansions to derive formula for the first derivative and the second derivative. For the first derivative, we do the subtractions between that Taylor expansion. And then for the second derivative, we are doing the additions between these 2 formula, and then we get different formulas. And this is the formula for the second derivative. Any question by so far? So let's take a look at here. So the next part, we are leveraging the standard difference formula to answer the questions here. We want to get a high accuracy formula for the first derivative. And remember this, we are not doing the second derivative this time. We are going to approximate the Fy(x)(0). That is the first derivative with order 4, fourth order accuracy here. And so let's take a look what we have. So we just derive the standard difference formula, and then it's with the Taylor expansion, and then that formula is telling us we would have. So let us just do some copy and paste here. This is the standard difference formula. And this is the standard difference formula. And the standard difference formula is this one, x0, and then E equals to fx0 plus h minus c fx0 minus h, and then divided by 2h. And this is the standard difference formula. And then now we want to use this standard difference formula to get the 4th order approximations of the first derivative. So let's see, how can we do this? Let's say this is the formula 3. And I am going to, instead of using the step size h, I'm going to evaluating the equation, the formula 3, and then with the step size h, 1/2 of the h. And then this time what I get is still a formula it's still an approximations formula for the first derivative, but here we are using the step size 1/2 h. And so I am just replacing all the h here with the 1/2 h, and then so that I have Fy(x0). And here, this is the center difference formula with the step size 1/2 h. And for the error time, because I'm replacing the h with the step size 1/2 h, and then so the error time, it should be h/2, and then do the square, and the 4th order term, we have C4, and then h/2, and then do the 4th order. And this is the, let's say this is the formula for. And now, if we want to get order fourth term, so let us simplify this fractions a little bit, because 102 to the square is just the 104. So this is just the 104. I'm going to simplify the fractions here. And we have C2. We still have C2H squared. And also, if we take the 102 to the order of 4, and then we got 16, 1/16. And then this one, it should be the 1/16. So could you combine the 3 and 4 to get a fourth order approximation? So the idea is cancellation. It's similar to what we have in the Taylor expansion. We do some subtractions, additions here, and then to get the cancellations. And if you take a look at here, we have, so we have second order term here, and then we also have second order term over there. So we want to remove this second order term in this two formula, and then what can we do? We can do this. We can, with the formula 4, we do the multiplications with the number 4, and then subtract this, and then subtract the formula 3. So we subtract the 4 times 4 from the, with this 3 here. And you will see that because we are multiplying the formula 4 with the 4, and then this error term would become C2H2, and then subtract the 3 formula, and then this C2H squared here, and then with that C2H squared there, and then we have cancellations with this 2 times, and it just goes away. So let's see if we do this multiplication and minus the formula 3, and then what can we get? So the calculations is the following. We have 4f prime x0, and that's on the left-hand side, and then subtract from the f prime x0 in the formula 3, and then we got, so on the right-hand side, actually we got the 4h with the half step size h, and then minus some things from the terms from the formula 3, and then that is with the step size h. And this time, I just say, okay, error term is 1/4, and then times 4, and then C2H squared, and then another another h squared term is coming from the formula 3, and then it is C2H squared. And then we also have the fourth order term, and then it's the 1/16 C4H4, and then minus the C4H4. And in this way, you will see that these two terms is they just go away. And so this time, let's do some calculations, some further calculations. On the left-hand side, we have 3 first derivative, 3 times first derivative, and then so we divide both sides by 3, and we get this. And now we get the first derivative, it equals to the fourth, the center difference formula with the half step size, and then minus the center difference formula with the step size h, and then divided by 3, because we have 3, the coefficient 3 on the left-hand side here. So we divide both sides by 3. Because these things are gone, and then we don't need to deal with them. And then for this one, I have, what do I have here? We have, I think I got a wrong calculation. So here we have 16, and this is the negative 16, 15, and then C4, and then H4, and then times 3 here. And this is the error term, but okay, and this is the error term for the approximation here. So now you will have, this is the error term, and then this error term is with the order 4. And this means that this formula, this equations means that we can approximate the first derivative with this formula, and then the error is this way. This error is order for fourth order error. And so now, what does it mean? We can write it in this way. So this is the, we can say this is the equation. You don't need to be very specific in the constants in front of that error. Why I'm not doing some copy here? Copy and paste. Okay, this is a formula, and then we are going to replace the constant, all the constant here with just a C. And so this is the formula, fourth order accuracy formula to approximate the first derivative. Let's see what we have here. For this center difference formula, actually it equals to this. So I am going to explain it a little bit so that you will see what we have in the data point. We have, so we are just replacing the h with the 1/2 h in the center difference formula, and divided by the 2 of the step size 1/2 the h, and then minus the center difference formula, and then divide the whole things by 3, and then the next thing is the error term. And this means that, so let's take a look at here for the forward difference formula, and then we just have one data point. We are using the x0 plus h or x0 minus h. What? Sorry, this is one moment, please. What?
Can you scroll up a bit? No, I just
Scroll up. Okay, scroll up. Okay.
Just a bit more. Is it not supposed to be 1/16 times 4?
The times 4? Oh yes, we need the times 4. That's why I think I have some miscalculations here. Yeah, I need to times 4 here. And so here we should have -3. So here we should have -3, then 4. This should be 4/3. And then divided by the 3, and then it should be 4C4/4, and then divided by 3, and then this one, it should be C4 over, and this one, it should be C4/4, and then we replace it with a constant C. Yes, you're right. I believe I missed something, coefficient there, and then, but I cannot figure out at that moment. Thank you. So let's go back to take a look at the formula, and then so for the first order term, for the first order approximations, and then we are just using one point theta. and then with the fx0. So actually we have two data here. We have f functions evaluated at this point, and then the functions evaluated at the x0. And this is the forward one, and then for the backward one, and then we have this. And then actually we are also using two data point here. Then for the center difference formula, we have second order accuracy, and then this time we are still using two data point, right? And then but we have the center, we have second order accuracy. And let's see, for here we have 4 data point, and it's so if we have the x0 here, and then we are going to approximate the first derivative at the x0, and then we are making use the data around it, and then that is the f function evaluated at the x0 plus h 1/2 h, and then the f function evaluated at x0 minus 1/2 h, and then also we are utilizing the data at the f functions at the x0 plus h. The f function evaluated the x0 minus h, and then which means that if we want to get a 4th order accuracy approximation, and then we are using 4 data points from the f functions. Does that make sense? So we have some. It doesn't mean that we can get a higher accuracy with the same point. We are using more data, and then so that we have higher accuracy here. But here you will see center difference formula is better than the forward difference formula or backward difference formula, because it's using 2 data points here, and but it gets the second order accuracy. But here we need more data point to get more accuracy. Any other questions? No? Wow. It's a second order, yeah, this one. So this is the Richardson's extrapolation, and then the extrapolations here, it means that we do some like interpolation here. We are using the step side in between, some data in between. So this is all the things about the numerical differentiations, and we finished this chapter. And congratulations, this is first chapter and first formal chapter in this class. And this is the useful things you learn in this class. And you would, if you are keep doing some numerical methods or some numerical computations with this finite difference methods or finite elements methods later on, and then you would repeatedly using these formulas. If you are doing such research, and then you will have all the things in your later life, your lives here. And this is the numerical differentiation. At the next chapter, we are doing some numerical integration. So in this chapter, we are using the formula to approximate the differentiation. And the next chapter, we are using some formulas to approximate the integrals. So the integrals we have here is the usual integrals we met over all the mathematics course. And sometimes the fx could be very complicated, and then you cannot get the antiderivative of it. And then so you cannot, so the usual way to do the integration is this way, right? And you are doing, if you are getting a function, and then you want to calculate it, and then you will get an antiderivative or the original function of it, and then you will evaluate the antidesert at the A and B point. And this is the way you calculate the integrals, right? But a lot of time this fx function is too complicated to get the antidesert, so that we can use the computer to do the calculation. And then a lot of time the calculator is using some numerical way to calculate it. And the numerical way is the numerical formulas here. The numerical formulas is we call it quadratures or quadrature rules. We partition the intervals into many parts. For examples, we have let me just draw here. So we have, for examples, we have the integrals, and then it looks like this way. And this is the f function, and then we are doing the same thing as the finite difference, and then we are partitions the interval. This is x0, or we have a and b here. So we are partitioning the intervals into n. So I call the first nodal point as x0, and then the last nodal point as xn, and then which means that I have n subintervals here. We have x1, x2, x3, and so on and so forth. And in the computer, it's actually using this quadrature rules to calculate the integrals over there. The integral, it means the area below the curve, right? And between the x-axis. So here we have the f function evaluated at the nodal points and one coefficient ai. But we are not sure what coefficients we are using here. We are going to derive some formula for the AI. We are going to derive some formulas, but that derivation is based on the interpolations of the polynomial, polynomials for the f function. And so this class, we are going to decide what is the AI coefficients, and then so that we have the quadrature formula, and then this quadrature formula is used to approximate the integrals we have here. And so the question is that we want to decide what is the AI, not artificial intelligence. This is the coefficients. And so, let's see. And this method of the quadratures, once again, is based on the interpolations polynomials. You can either use the Newton's form, Lagrange polynomials, or the Taylor, not Taylor expressions. I think it's just the Lagrange or Newton's forms. We would use these two in this class. So let's get some idea how to get the quadratures formula here. Let's go back to the very beginning from the calculus class. When we first talk about the integrals, we are defining the integrals in this way. We are using the Riemann sum. Do you remember this? We are using the Riemann sum. We partition the intervals. We partition the interval a and b into n parts, n smaller parts. And we are using so for example, we have the x0, x1, x2, x3, x4 here. And we are choosing some representative point between the interval xi-1 to the xi. That is, for the first interval, we are choosing some representative point between the x0 and x1, and then we put it to here, and then f you evaluate it at the representative point, and then times the length of the interval. And then we do the summations for all the subinterval here, and this is the Riemann sum. The definition of the integral is letting the, so let's say we have the maximum value of the length of the interval, and let's take the maximize of the length of the subinterval, and then the integral is defining in this way. So letting the or the subinterval, the length of the subinterval going to 0, and then taking the limit for the Riemann sum, and then this is the definition of the integral. So actually, we can use all this area, the sum of this, all the right triangle, rectangles, the sum of the rectangles area here to approximate the area, the interval. And also this is the lower sum and this is the upper sum. Lower sum, which means that the representative point is the left endpoint of the subinterval. And for the upper sum here, it means that we are using the right endpoint to be the representative of the interval here. Actually, you can use such a things to be a formula to approximate the integral. But now, let's say we want to do one simple situation. We only have 2 points and then just one big interval. So we just have we have just one big interval here. And this is my x0 and this is my x1. I'm going to use this this trapezoid area to approximate the integral here. The integral from a to b for the x function. And so here, if we calculate the trapezoid area, and then it should be, the area is the sum of the size fx0 and then fx1, and then do the 1/2, and then times the size here, the length of this size here, and then that is the b minus a. And we are going to use this area to approximate the integrals fx on AB interval. This is one simple situation. We are going to using the area, the trapezoid area, to approximate the the interval here. But maybe I can help you to do some coding homework, and that is using the lower sum and upper sum to approximate the interval as well.
I have a question for the lower sum. So is it not always using the left endpoint? Because based on the graph above, for like the fourth triangle, it's actually using the right endpoint.
I think, let me see, the lower sum. Okay. I think it has, so here, okay, the lower sum here is defined, in this picture is defined the I think is defining with the smallest value and biggest value, but what I want is not this picture, is the left sum and then the right sum.
Oh, so this one is actually not that accurate.
Yeah, not what I'm describing.
Okay.
Because maybe I just searched for a wrong picture. Yeah, what I want is the left endpoint and right endpoint representations, because the homework would have the question 3, and then question 3 is kind of difficult. I'm going to give you an option to do some coding homework for that question 3, which is utilizing the left endpoint and right endpoint to approximate the integral. It's actually using the Riemann sum to approximate it. Okay, thank you. Maybe I need to change these pictures for the next semester. Good, thank you for your suggestions. Okay, so let's go back to our discussions. We are using the trapezoid area to approximate the integrals here. What we are concerning about is the error of these approximations. This is in the same way when we talk about the numerical differentiations. When you have formula to approximate something, and then we care about the errors. What is the error, right? And so now, if we are using the trapezoid area here, trapezoid rule here, to approximate the error, to approximate the integral, and then what is the error of such approximation? So now, the general way to get the, let's go back to the very beginning. We say that if we want to get the quadrature rules, and then the quadrature rules are mostly based on the interpolation polynomials. So now let's get to have, so now we have 2 points, right? And then we are going to derive the trapezoid rule by using the polynomial, the interpolation polynomial here. So for example, we have the Lagrange format of the interpolation here. This is something from your previous classes, the 104A. And if we have n+1 node points, and then the Lagrange interpolations is in this way. We have the basis function here, and then we have the coefficient here, and then the coefficient is just at xj. And the polynomial, the basis here is just this way, in this format. And then for the subscript j, and then you will see we don't have the diameter for the, so we are changing the, from here, we have a product here, and then you will see we are changing the index k here. The k is from 0 to n, but for the subscript j, we are excluding the k equals to j here in the diameter. So this is the basis function. And so for example, we would go to the one example for the Lagrange form, in case that you haven't known the Lagrange polynomial before. And then for the error, this is the error for the Lagrange interpolations for the fx function. And if you are using n+1 node points, and then this is our error for the Lagrange interpolation, and then we have the n+1 derivative here, but we have a c point, which is depending on the x you have, and the c x is in between this interval. And because the node points is in between the a and b, so the c point is also in between the a and b. And now the idea is, if we want, this one, the p and x is the is approximating the fx. This is the Lagrange polynomial to approximate the fx, right? But this class is asking, we want to approximate the integral of the fx, right? And so now what we are going to do is to integrate the p and x, and then use the integral of the p and x to approximate the integral of the fx on the interval a and b. So now if you do the integration, and then what would we have is, so let's do the integration here. We have the x function, right? And so if we are going to do the integration here, what do we have? We have the fab pn x dx, and then we are doing the integrations for the x, so which means that this equals to the integrations ljx dx. And so now you would get, this is the approximations for the integral of the fx. This is the approximations for this one. And so I have already write down the formula in another way. So this is the quadratures with the order n, and then the aj. I just use the aj to replace to be the notations for this one. And then the aj is the coefficient, because after the integration, and then you will get just one constant here. So this is the coefficient, and then the fxj is something from the formula as well. And so now this is the approximations for the integrals. And once again, we need to answer the questions, what is the error of these approximations? So we have this one is the approximations for the f, and then this is the approximation for the Lagrange polynomial. And so if we are using this Lagrange polynomial and then do the integration to get the approximations for the integral, so here, hence we have the error. The error should also be the integral for the error term here. So the error term should be, the error term is also the integral. The error term is also the integral, and then it's just the integrations from a to b for this functions, this error function, and it's here. Any questions? Max my level, okay. Zoom in a little bit, okay. Is this one, if you cannot, if this one is too small, and then this one is just the integrations from a to b here. Because we are doing the integration, so let me just write down here. The idea is pretty simple. So we have the fx, right? And then we are using the pnx to approximate it. And then we have the error term. And so now we are going to approximate the integral x dx. And then by doing the integration of the pnx, the pnx is the Lagrange polynomial here. And also you can use another form, the Taylor expansion, or the other things for the Newton's form. And then so the error term is from the error of the interpolation and then doing the integral. And then for the pnx here, the pnx is just the nj0, and then the coefficient is the value evaluated at the xj, and then the ljx is the basis. And then the error term is the error term, I say the error for the interpolation, and then it's the pi, this is not the pi, this is the product, not the product here. We have the fn plus 1, and then divided at cx, and then plus 1 factorial, and then now we have the product, the big product here, and then it's from the 0 to the end, x minus the x up. And this is the error term for the interpolation. And if we want to get the errors for the integral here, and then it's just the integral of the error term here. So now, this is a general rule to get the quadrature. So now, what we asked in the very beginning is to get the error of the approximations for the trapezoid rule. So now let's use this Lagrange polynomial to derive the formula first, and then to get the error at the same time. And because we have two nodal points here, and then the Lagrange polynomial for the Lagrange interpolation for the fx is exactly the line connecting the fx0 and then the fx1 over there. So the Lagrange polynomials, if we write out the Lagrange polynomial, and then that is exactly the straight line, what the straight line representing here. So now, once again, let's take a look at let's go back to the Lagrange polynomial. The Lagrange polynomial, because we have only two nodal points, so we have which means that in case you haven't known this before, the Lagrange polynomial, so we have 2 points, right, x0 and x1. So now we have the degree 1 polynomial, and then we have 2 terms in the formula. We have we need to replace the j with 0 and then replace the j with 1, and then there are 2 terms in the P1x. And so for the first term, I have fx0 is the coefficient, and then for the basis function, I have x minus x1, and then divided by x0 minus x1. I'm just substituting the j with 0 here, and then that is the L0x. And you would need to take a look at the formula for the Ljx here. And then with the n equals to 1 here, I'm pointing to this one. So I'm doing so here we have L0x, and then it's just the product because is k, right? To the 1, and then k does not equal to j. So this is the x minus the xj, xk minus the xj. And this equals to, which means that we are using the 0 here. And then so we have x0 here, and then minus x1 because we cannot let the k to be 0. And so here we have x minus 2 minus x0, and then this is the L0x when we have only 2 nodal points. Does it make sense? This is something from the Lagrange polynomial format. So let me see, am I right here? We cannot let let's see, x1. So I'm making some mistake here. It's xj first. It should be the xj. I'm copying the wrong formula. Let's see, xk. Let me see, it's the xk here. This is xj, so this one is x0, this is x1, and this is x1. We can let the k to be 0 because the j here is just a 0. So this is k does not equal 0. So we have such a formula for the L0x, the first basis function, and then we could do the same things for the second term, and then that's fx1, and then you substitute the j with the 1, and then that would be x minus x0, x is 1 minus x0, and then this is the Lagrange polynomial for the fx function. This is the P1 Lagrange polynomial for the fx. And we have 3 minutes left. And this is the P1 function, and this is an approximation. This is the Lagrange polynomial with order 1, with degree 1. for the fx function. And so we have the P1, right? Let's follow the process we have here. We just say we have, how can we get the quadrature root? We are doing the integral for the Lagrange interpolation, and then we get the formula for the approximation. And then we also have the error term, and then the error term is just the integration of the error term in the Lagrange interpolation. And so now let's take a look. We have 2 minutes left, and then never mind, we can take a look what's the integrations here. So let's see. So first, the fx is just the p1x, and then with the error term, and then the error term here is the, so we have x0 and then x1. So the error term here, we are just replacing the 1 here, and with the 1. So we have 2 factorial in the denominator, and then we have a second derivative in the numerator. So we have 1/2 factorial and a second derivative, and evaluate at the c x. And then we have x minus x0 and x minus x1. And this is the error for the Lagrange interpolation. Error for the Lagrange interpolation. And then this is just the Lagrange interpolations for the fx. So the next class, we would continue our calculations. We are doing the integrations on both sides, integrate the both sides over the interval a and b. And that's all the material we have for today. In the next class, we will continue our calculation and getting the formulas for the quadrature root and the error for the quadrature root here. And class is over. If you have any questions, you can come over here.
可以呀，这第4题，就是第4题，我看你那个发了 Taylor 上面那个 hint，但是我用那个 Taylor